Okay, so suppose I'm given a function f of xy is equal to x squared minus 2xy plus 2y, and I'm asked to find the absolute maximum minimum over the region bounded by the rectangles, or the rectangle, and they give me some corners 0, 0, 3, 0, 0, 2, and 3, 2. So I'm asked to find the absolute maximum and minimum. First, I'm guaranteed that an absolute maximum and minimum will exist because f of xy is a nice continuous function. And also I have this region is a rectangle, so it's closed and bounded. So I'm able to conclude that there will indeed be somewhere that has an absolute maximum and somewhere that there will be an absolute minimum. So I'm going to go ahead and actually calculate that now. So we're going to break this down. Why don't I draw the region first? So these are the points that I'm allowed to, the region that I'm allowed to select x and y values for. It's a rectangle. It has vertices 0, 0. So this is the point 0, 0 right here. This is the point x equals 3, y equals 0. This is the point up here, x equals 3, y equals 2. And this point here is x equals 0, y equals 2. So this is the region R that I'm going to see where on this rectangle, by choosing x and y values, so this is the y-axis and this is the z-axis, by choosing values of x and y that are restricted to this area here, where would I find the maximum value for my function and the minimum value for my function if I'm restricted to only choosing x's and y's from inside of this rectangle? So I'm going to break it down into 4 parts. The first part is find the relative max and min, max and min inside the rectangle. So I'm going to find all of the places that I could have a max or min inside the rectangle. The second thing that I'm going to do is find the absolute max and min, on boundary 1, and I'll call this boundary 1. This is boundary 1 here. Oops. I'm going to call this boundary 2. I'm going to call this boundary 3. And I'm going to call the left-hand side here boundary 4. So the second part I'm going to do is try to figure out what the absolute max and min is on boundary 1. The third part I'm going to do is figure out what the absolute max and min on boundary 2. The fourth thing I want to do is figure out the absolute max or min on boundary 3. And then the fifth thing I want to do is calculate the absolute max and min on boundary 4. And so essentially I've broken the search down into finding the max and min on the inside, and then finding the absolute max and min on each of the boundaries, and then at the end I'm just going to take whichever one is the biggest and whichever one is the smallest. So this is my game plan. So let's get to it. The first part, so let's find the relative max and min inside the rectangle. So to find the relative max and min of my function, I am going to find the critical points inside of R. So I'm going to find the critical points. Oops. I'm just going to write CP for critical points. Find the critical points inside R. To do that, I do the partial derivatives with respect to x and y, and I set them equal to 0. So fx, the partial derivative of f with respect to x, is 2x minus 2y, and the partial derivative of y, or of f with respect to y, is negative 2x plus 2. And to find the critical points, what I want to do is set these equal to each other. So the first equation, maybe I'll call it equation A. I'm going to have 2x minus 2y is equal to 0, and equation B is negative 2x plus 2 is equal to 0. And so from these two equations, I notice from equation B that the only place that this is true is when if I move the 2x over and divide both by 2, I get x equals 1. And of course, if I take the x equals 1 and put it up into this equation here, what I find is when x equals 1, it's 2 minus 2y equals 0, which means y is equal to 1 as well. This is the only values of x and y that make both of these equations 0, so the only critical point only critical point on R is the point 1, 1, which is laying somewhere around here. And so what I would like to know is, well, what is the actual value of the function at that point? The value of the function at 1, 1 is equal to, if I go back up and take a look at my function, x squared minus 2xy plus 2y. So I would get x squared, which is 1 squared, minus 2 times x times y, plus 2y. So plus 2y. So you get 1 minus 2 plus 2, and so the answer is 1. So this is the only place inside R that will actually be a max or min. It's the only place that there's a critical point, and so the value at that point is equal to 1. So that's our first kind of candidate for the absolute max or min on this whole entire region. All right, so the second part, the absolute max and min on boundary 1. Okay, so part 2. Let's calculate the absolute max and min on boundary 1. Now, if I'm on boundary 1, I'm on the x-axis right here, and so y is equal to 0. So on boundary 2, y is equal to 0, which means my function, the actual function, I can replace y equaling 0 everywhere in my function, because as long as I stay on this boundary, I'm forced to have y equals 0. So if I plug in 0 into my function, 0 for y into my function, I'm left with x squared, just x squared. And so I'm going to name this function something. I'm going to call it f sub b1. It's a function of x, and all it is the function x squared. So essentially this is the function of one variable. There's only one variable now in this function, the variable x. And so now what the name of the game is what I would like to do is figure out the absolute max and min of this function, fb1, as x goes from 0 to 3. So absolute max and min on boundary 1. It has 2 steps. So step 1, or I guess step little a, find the critical points. Okay, so this is just a function of one variable x, and so I calculate the critical points. I take fb1 prime and set it equal to 0. So that becomes 2x is equal to 0, and x equals 0 is the only place that this is true. However, this isn't a critical point, not a critical point. And the reason it's not a critical point is because it's actually on the boundary. It's x is allowed to go from 0 to 3, and so this is actually at x equals 0, so it's not technically a critical point. The next thing that you want to do in trying to find the absolute max and min of a function over an interval is we're going to evaluate f of b1 at the endpoints. So we're going to, the endpoints of our interval, x is allowed to go from x equals 0 to x equals 3, so we're going to evaluate this new one variable function at 0. So I sub in x equals 0 into my new function, and I get, well, 0 squared is 0. And the function at the other endpoint, which is x equals 3, is 3 squared, so that equals 9. So on just this little strip here, on just this boundary b1, so on b1, the absolute max is equal to 9 right here, and the absolute min is equal to 0. Okay, so I've just calculated what the absolute max and min of this function is as long as I stay on boundary 1. And now all we're going to do is repeat that same calculation for the other 3 boundaries. So this is going to be part 3. Part 3, I'm going to do boundary 2. So on boundary 2, let's take a look at what boundary 2 is. It's this line right here. On boundary 2, we notice that x is always equal to 3. So as long as I stay on boundary 2, I have that x is equal to 3. So what I can do is now I'll go down here on boundary 2, x is equal to 3, which means if I sub in x is equal to 3 into my function, y of course can be anything between 0 and 2. What do I end up with? Well, let's go ahead and take a look at our function. X squared minus 2xy plus 2y. So if I sub in x equals 3 into this, I get 9 minus 6y plus 2y, which is 9 minus 4y. So as long as I'm on boundary 2, my function actually ends up just being a function of one variable. It's just the variable the variable y. And so I'm going to name this something. I'm going to call this the function on boundary 2. And it's only a function of y, because all I have now are just y values, and it's 9 minus 4y. So now we do the exact same thing we did on boundary 1. Let's calculate the absolute max and min of this function, fb2. So absolute max min of the function b2. Okay, so how do you calculate the absolute max and min of a function of one variable? Same way we did it before. There's only 2 points that can happen. It can happen at the critical points of the function. So to calculate the critical points, we take the derivative of this with respect to y. Well, it only has one variable, so we do f prime of y is equal to 0. If we take the derivative of this with respect to y, we get negative 4 is equal to 0. This is not possible, so there is no critical point along this boundary either. And then the other thing we do is we plug in our endpoints. So what are the endpoints? What numbers can y be? Well, y could be 0, and y could go all the way up to 2 on this boundary. So y is between 0 and 2. So let's plug in our endpoints. The function along b2, when you plug in the endpoints, y equals 0, is 9 minus 4y. So 9 minus 4 times 0 is 9. And the function b2 at the other endpoint, where y is 2, plug in 2, you get 9 minus 8, and that is equal to 1. So on b2, on boundary 2, the absolute max is equal to 9, and the absolute min is equal to 1. Okay, so that's just along boundary 2. So now let's do boundary 3. So part 4 is, let's do boundary 3. On boundary 3, let's take a look at what boundary 3 looks like. Boundary 3 is the top here of the region. Along boundary 3, y is always 2. X can go between 0 and 3, but y is always 2. So on boundary 3, y is always equal to 2, which means when I plug that into my function, so I can let x be anything between 0 and 3, but because I'm on boundary 2, I'm fixing my y value at 2. So if I plug this up into the function, if I take a look at what my function is and I plug y equals 2 into this, I would get x squared minus 4x plus 4. So x squared minus 4x plus 4. So this is x squared minus 4x plus 4. This is all one function of one variable now. The only variable we see is x, so I'm going to call this the function on boundary b3. It is only a function of x. It's x squared minus 4x plus 4. So now, just like the other two boundaries, the name of the game is let's find the absolute max and min of this new function, the function on b3, which is just a function of x. So just like we did before, and just like every other time that we want to calculate the absolute max and min of a function of one variable, there's only two kind of places it can happen. The first place is critical points. So let's calculate the critical points of fb3. So we take fb3 prime and set it equal to 0. Of course, the derivative of fb3 is 2x minus 4. Set that equal to 0. Solve for this and we get that x equals 2. Okay, so that means there was a critical point along this boundary at x equals 2. So the value of the function of fb3 at x equals 2, well, I go to fb3, it's this, and I sub in my critical point now. I sub in x equals 2, I get 4 minus 8 is negative 4 plus 4. So the value at the critical point along b3 is just 0. The only other places that an absolute max or min can happen along this boundary is at the endpoints. So we have to evaluate fb3 at the endpoints. So fb3 when x equals 0 is plug in 0 into fb3 and I get 4. Plug in the other endpoint, fb3 at 3. I get 9 minus 12. which is -3 plus 4 is equal to 1. So on B3, the absolute max is equal to 4, and the absolute min is equal to 1. Okay, almost there. The last thing we need to do before just comparing all our values, so part 5 is we need to figure out what the absolute max and min are on boundary 4. So if we go up to boundary 4, let's take a look at what boundary 4 looks like. On boundary 4, we have that x is always equal to 0. So if we plug in x is always equal to 0, we end up with the function 2y. All right. So along boundary 4, x is always equal to 0. On B4, x equals 0, which means when I plug in x equals 0 into my function, y can be anything between 0 and 2. What I end up with is just the function 2y. So I'm going to call this the function along boundary 4. It's just a function of y, not just the function 2y. So now, just like the other boundaries, the name of the game is let's figure out what the absolute max and min is of this function as a function of y. And as always, there's only two places where this this absolute max and min can happen. The first one is at critical points. So critical points along this boundary. So we take the derivative of b4, so f b4 prime, set it equal to 0. The derivative is 2, set that equal to 0. That's not possible, so there are no critical points. Not possible. Of course, 2 cannot equal 0, so that means no critical points. So the only place that an absolute max or min can happen along this boundary is at the endpoints. So I'm going to plug in the endpoint y could equal 0 into my function. FB4, I get 0, and if I plug in the other endpoint where y could equal 2, I plug that in and I get 4. So along boundary 4, the absolute max of this function is 4, and the absolute min of the function is 0. So on B4, the absolute max is equal to 4, and the absolute min is equal to 0. So now essentially what we've got ourselves is we know what the biggest or the highest point or lowest point on inside the region is. This is the first thing we calculated. The function had a value of 1. And then we've actually gone and calculated what the absolute maxes and mins are on every single one of these boundaries. So the only thing that's kind of left to do is compare which one was the biggest and which one was the smallest. So inside we found a value of 1. Along boundary 1, the max was 9 and the min is 0. So far I would say that the absolute min is 0 and the absolute max is 9. Here we have that the absolute max is 9, the absolute min is 0. So our biggest value we found so far is still 9, and the smallest value we found so far is 0. If we go to boundary 3, we had 4 and 1, so again we're still bigger. The absolute value, or absolute maximum still is 9, and the absolute minimum still is 0. And here we have 4 and 0. So we conclude that that the absolute maximum of our function f of x, y on this region is equal to 9, because that is the biggest maximum that we found in all of our inside the region and in all of the boundaries. Similarly, the absolute minimum of f of x, y on R is equal to 0, because 0 was the smallest value we found on all of our boundaries and inside the region R. So this is the absolute max. The absolute max is 9, and the absolute min is 0.